In this presentation, we're going to look at rates of reaction and how we measure it. So let's remind ourselves of the factors that affected the rate of reaction. First of all, concentration. If a chemical was more concentrated, there are more particles there, and so there are going to be more collisions, and more collisions means more reactions. But temperature also has an effect, because if the temperature is too low, then not enough of those collisions have enough energy to overcome the activation energy. There has to be a higher temperature so that more particles can take part in those collisions and those reactions. Surface area was also important, because with a greater surface area, just more of your reactants are coming into contact with each other. And of course, catalysts can increase the rate of reaction by lowering the activation energy for those reactants. And if it's a gas, pressure acts in almost the same way as concentration. With the greater pressure, it means those particles are actually colliding more frequently and with more energy. So you might remember at GCSE the marble chip experiment, where pieces of calcium carbonate were put into hydrochloric acid and carbon dioxide gas was given off. Now, in this experiment, the explanation for why the various different factors affected the rate of reaction was based on the whole idea that it was to do with collisions. You wanted more collisions for a greater rate of reaction, and they had to be of high enough energy to overcome the activation energy of those reactions. And that is why temperature, concentration, the presence of a catalyst, surface area, and in a gas, pressure affects the rate of reaction. You might also remember that there was different ways in which we could gauge the rate of reaction. So it could be the rate at which gas is produced. If the products of a reaction are in the gaseous state, then we could measure with a gas syringe just how rapidly that is being produced. Alternatively, we could look at how the mass changes with time. Another one is you could look at the disappearing cross as a precipitate forms in your solution. Either way, all of these are basic ways of observing the reactants being used up or the production of a product. So where this gets more complicated is in those situations where perhaps it's not so obvious. Perhaps the only way you know that a reaction has taken place is because of a change in concentration of either the reactants or the product. Now, in those situations, in solutions, there is a way of working it out. The rate of reaction can just be found by the change in the concentration divided by the time taken for that change to take place. You can see that the change in concentration is going to be measured in the units of concentration, which is moles per decimeter cubed. And if we divide that by time, measured in seconds, then the unit of the rate of reaction is going to be moles per decimeter cubed per second. Now later on, we're going to represent this with this formula notation, where the triangle represents change, and you can see their square brackets represent the concentration of a particular chemical A. And so the rate is equal to delta, that's the triangle, square brackets A divided by delta T, where delta T is the time interval over which we are measuring. And I suppose we can't skip past this bit without giving our due respects to Søren Sørensen, the Danish chemist who worked in the Carlsberg laboratory, and his pioneering work on concentration of, well, in this case, the hydrogen ion, was the basis behind our understanding of the pH scale. Now, it's his notation that we are using here and that we will use later. To fully understand how the concentration changes, it makes sense to draw a graph of concentration against time. Now, this graph here is the concentration of the reactant, something that is being used up. You can see initially there's a lot of reactant, and as time goes on, there's less and less and less. That's because there's fewer remaining to react. the gradient of this graph, if you consider that the change in the y-coordinate would be the change in concentration, and the change in the x-coordinate would be the change in time, then the gradient of this graph would be the change in concentration divided by time, which would be equal to the rate of reaction. You can see on this graph that the actual line is not straight. It means that the gradient is changing with time. To start with, the gradient is very steep and it becomes more shallow later on. Now, to measure the rate of reaction requires us to draw a tangent line at the point of interest and measure the gradient of that tangent line. If the gradient is changing, it suggests that the rate of reaction is changing. In this case, the rate of reaction is slowing down, and that makes sense because more and more of the reactants are being used up. And perhaps the opposite of that graph is this one. If on the y-axis we plot the concentration of the product instead of the reactants, you can see that it changes the direction of the graph. Now, rather than going down, this graph is going up. It starts at 0 because before the reaction has begun, there's no product. But as the reaction takes place, the product is produced, and so it reads on that y-axis scale. You can see here that it's steep to start with. When there is an abundance of reactants, the rate of reaction is highest, and so you can see it is steepest to begin with. But as more and more of the reactants are used up, the rate of reaction decreases and the amount of product produced decreases, lowering the gradient and lowering the rate of reaction. The key to interpreting this diagram is to imagine what the reactants are doing in order to form this. With both the concentration of reactant graph and the concentration of product graph, we can find the initial rate of reaction by drawing a tangent line at the t=0 point. You can see there on the left where the blue dot is that what we're doing is we're measuring the gradient initially to find out what the initial rate of reaction is. But you will notice on one graph we're getting a negative gradient. The slope is downhill. On the other graph of the same reaction we're getting a positive gradient. And that's just because what is this the rate of? One is the rate of the reactant disappearing, and the other is the rate of the product appearing. So one of them is going to be the negative of the other. So here is an opportunity to consolidate, pause the video here, and answer these questions.